And there's a little problem actually with this, and that is the reason Schrödinger, and potentially the lesser known reason as to why Schrödinger made this thought experiment. It was not to always talk about superposition, it was to actually highlight a problem, which is that, well, obviously when you check inside the box, the cat must be dead or alive, of course. The poison's either escaped or it hasn't. But what Schrödinger was trying to get at here was the paradox. When exactly does the superposition end and only one outcome remains? Now, of course, when you open the box, you instantly know, right? But is it where you open it 1 centimeter and then the superposition leaves? Is it when you open it a crack? Is it when you intend to open it? Or does it have to be a human? Is the superposition, could a monkey do it? Could an insect do it? Could just a tiny atom destroy the superposition? When is it that the superposition ends and only one outcome actually can be observed? And we call this the measurement problem, and it's still unresolved to this day. No one really knows how superpositions are destroyed by measurement. There's a lot of different theories out there and they get very complex, but ultimately we haven't found the best and most convincing theory yet. It's difficult. Anyway, let's go back to the Schrödinger equation, because this is the most important thing basically in quantum mechanics. It is this equation. And so what's amazing is that, well, Bohr initially said, okay, well, I think my sort of solar system atom is good here. I think it works, and in some cases it does. But Heisenberg said, oh, well, there's some uncertainty about where your electrons are. We can never quite know where the electrons, what the position and the momentum of the electrons are at the exact same time. So they can't be in these sort of well-defined orbits, because they are inherently a quantum thing and they are inherently uncertain. So you can't represent it as simply as that. And this is where Schrödinger came in. So knowing that electrons can't have simultaneously an exact location and an exact momentum at the same time, they must be in a sort of cloud of possible locations, a cloud of probability, right? They kind of probably exist most of the time here, but then we might also find them here, etc., here, etc. And we call them orbitals. That is what the cloud of possible locations is called, orbitals. And what do single electron orbitals look like? They look like this. It's very beautiful. You can kind of see spheres, you can see groups of spheres and donut shapes and interesting formations, and these sort of coloured donuts, all of these shapes show the 95% and above probability zones. So this is where the electron is 95% likely to be found. Technically, with quantum mechanics, there is no limit to where an electron could be found, to the uncertainty of an electron's positional momentum. So technically speaking, there's a 5%, everything outside of that is a 5% chance of being found, and that doesn't end, that extends throughout the entirety of space. But the point is, these are where you're very, very, very likely to find them, and that is what an electron is like. And each layer, so if you think of it like a cake, we've got the top layer up here, we've got the second layer here, we've got the third layer and the fourth layer. These are the energy levels of the electrons, a bit like Bohr's orbits. These are the quantized energy levels. So you have the first energy level, the smallest energy level. You have the second energy level where electrons are slightly more energetic, the third energy level, and so forth. So it kind of, Bohr wasn't completely wrong, but he wasn't completely right either. How does it tie in with Schrödinger? Well, he said Schrödinger was the one that had created these beautiful spheres and donuts. He was the one that calculated the wave function probability. That's what we call it, because the wave function is the quantum system. And so he came up with, okay, I'm going to work out the wave function of an electron. And he treated the electron like it was a wave. Even though people thought it was a particle, let's invoke that duality that we were talking about earlier. Let's treat it as though it's a wave, because it's something that moves. It's both a particle and a wave, and that allowed him to create a wave function, and then that allowed him to solve for the energy levels of the one electron system. Hydrogen generally Not always, but usually has one electron. So he solved for the electron wave function of hydrogen. And these solutions, they gave him probability distributions, which when you plot them in 3D, gives you these beautiful shapes, these orbital shapes. So this is what Schrödinger worked out. And that is the true nature of an electron. It is a cloud of probability. And the same kind of goes for all quantum particles. So in the nucleus as well, they're made up of nucleons, which will also, experience quantum effects. So they won't be localized in one point either. And the things that make up neutrons and protons and these nucleons, they will also experience quantum effects. So the main takeaway from this is that atoms are quantum, and that everything inside them does not exist exactly in one place. They exist in a world of quantum probability. So let's now go on to talk about Paul Dirac. He's a British physicist, or I guess was a British physicist, will always be a British physicist, but he's not alive with us today. And he was known for starting the process of unifying special relativity, which came from Albert Einstein himself, and quantum mechanics. And this was a huge deal. We needed this because by combining the two together, we can create something that's even stronger, a more robust theory that can describe more phenomena. And so because he was able to achieve a relativistic, meaning a special relativity encoded description of the wave function of an electron, which Schrödinger had failed to obtain. This was something that was, it would take a while to discover, and Schrödinger had not obtained this. Paul Dirac, coined it the Dirac equation. So it is basically the child of special relativity in quantum mechanics. And it also predicted the existence of the positron. And maybe a lot of people might not be familiar, but the positron is the antiparticle of the electron. So it has positive charge. And when I mean to say antiparticle, I literally do mean antimatter. I mean the opposite of matter. So we're all made of atoms, we're all made of electrons and nucleons, etc. There's the anti-version of our particles, and they exist in the universe. Not to the exact same proportion as matter, but the point is there are the anti-particles of our particles, and they do exist, and this is the anti-particle of the electron. So now we're getting into the real kind of great results that came from all of these quantum theories, and this is something known as the Copenhagen interpretation. So Niels Bohr, Werner Heisenberg, Max Born, all these amazing physicists. Einstein would have Einstein's met Bohr, and Schrödinger was there, and they all kind of knew each other in a weird way. They couldn't agree on the interpretation of quantum mechanics. So they agreed that their theories were aligned and correct, and they were enjoying quantum mechanics as it started to come out, but they couldn't agree on how to interpret the results. What does it mean for the universe? And so people came together to try and unify the points that they did agree on, and we called this the Copenhagen interpretation. And so put simply, the Copenhagen interpretation can be kind of described by these main points. So a system is completely described by its quantum state, the wave function. A quantum state evolves according to Schrödinger's equation. So that's how it changes in time. Events in nature are essentially probabilistic, which is Born's rule. So anything that has a quantum state will essentially not have a guaranteed probability. It will not be guaranteed to do anything. It will be based on some roll of the dice, if you will. And that's why Einstein said, famously, he said, God does not play dice. And what he was saying, he was struggling to come to terms with the idea that things in nature could be probabilistic in the quantum world. And matter can also be both a particle and a wave. And there is that duality. We call it, the particle wave duality. Exactly. And it's the idea that, matter can act like a particle sometimes, and it can also act like a wave sometimes. It's trippy but true. And why Copenhagen? Well, the Niels Bohr Institute was founded at the University of Copenhagen by, of course, Niels Bohr in 1921. And famous physicists from all across Europe and the world really came to discuss new quantum theories. And today it does lots of research in different disciplines: astronomy, geophysics, particle physics, biophysics, and much more. So it's a huge communal hotpot of science. So now we're going on to the more advanced and more modern, very modern concepts in quantum mechanics, and this is quantum field theory. It is the quantum way of describing fields. You might be familiar with, electric fields. You might be familiar with magnetic fields, electromagnetic fields, and this is the quantum way of describing them. And so, by applying quantum mechanics to fields instead of single particles, this results in quantum field theories. So, for example, quantum electrodynamics, which has been incredibly successful and is able to describe exactly how electric fields work and how light interacts with matter in a quantum way. It's very good. Quantum chromodynamics, which is to do with the interactions of nuclei. So this is the nucleus in the atom, and these are to do with the fundamental tiny interactions of the building blocks inside the nucleus, and lots of famous people have worked on these theories throughout their entire lives. Richard Feynman, Freeman Dyson, Shinichiro Tomonaga, Paul Jordan. These are all very, very famous people who've dedicated their lives to these fields, and yeah, it is a incredibly complex but wonderful field, and to understand, and yeah. But where does quantum computing come into this, right? So we've talked a lot about quantum mechanics, but surely that quantum computing must have come from this in some way, and it's true. There were a lot of people that would work on unifying quantum mechanics with the idea of computing and computers. So Stephen Weisner, Alexander Holevo, and Charles Bennett, and so many more people. This is all in the 1980s, where people started realizing, quantum things are difficult to try and simulate with normal computers, right? We need to create a computer that's really good at simulating the true nature of our world, which is quantum. Well, if we need something to simulate something quantum, we should probably make it quantum itself, right? Try and make it easier on ourselves. Why try and do it with something different? Let's do it with the same stuff, right? And so this is commonly known as the Feynman moment, although also Paul Benioff was also there and at this kind of conference, which is the first conference on the physics of computation at MIT in May 1981. So Paul Benioff is the one on the left, Richard Feynman is the one on the right. And Paul talked about some of his earlier work where he was already talking about the Turing machine, and he's talking about, which is based on Alan Turing and his computer, and he's talking about how computers, in theory, they could utilize the rules of quantum mechanics, right? And that could be advantageous in some way in understanding and simulating quantum systems. And Richard Feynman then went on to say, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. So he was saying, since nature is fundamentally quantum, there's no way we can simulate nature and actually understand anything about it unless if we make our computers quantum mechanical themselves. So let's make our computers out of quantum stuff. And it should be exciting. So thank you very much for joining me for the first video series, or first video episode, and I very much am looking forward to releasing more and more of these videos, and we are going to be diving straight into quantum computing in the next episode. So I very much hope to catch you there. Hope you have a wonderful day, and I will see you later. All right, thank you. Bye bye.